we delve a little bit more into the equation y equals a times b to the x. Again, a is going to be the starting point. That looks great. And b is going to be the multiplier. So that's important to keep that in mind from Chapter 5. So in Chapter 2, you looked at the multiple representations such as table, graph, equation, or situation of linear functions. In this chapter, we're going to use multiple representations to learn more about multiplier and y-intercept of exponential functions. So same thing, we'll be getting some word problems, we'll have some graphs, we'll have some tables given the equation, and we'll just sort of go back and forth between the other. So let's look at some of the connections between the multiple representations of an exponential function. Arnold dropped a ball during the bouncing ball activity and recorded its height in a table. Part of his table is shown right. What is the rebound ratio of the ball, and where did he drop it from? Well, when we kind of look at this, we know that we need this term right here because this is going to be the A term right here, whatever this ends up being. And we also know that b is going to be whatever we're multiplying by. So I would suggest that you use some algebra. I always encourage people to write this out because it can be confusing. Sometimes kids just divide one by the other, but they don't know why they're dividing one by the other. We know that 84.5 times b is going to equal 67.6. And what this equation allows us to do, this just simple little algebraic equation, is it allows us to make sure that we know we're dividing the right term by the right term. So I'll just get b is going to equal whatever 67.6 divided by 84.5 is. And I am going to get 0.8. So I know that I'm just going to multiply by 0.8. And if I want to make sure that that's true, I'll multiply 67.6 by 0.8 just to verify that I do indeed get 54.1, which I do. You can see it rounds to 54.1. So I have my b of 0.8 here. So if I'm multiplying in this direction by 0.8, what I need to be doing in this direction is I need to be dividing by 0.8. So I'll go here, I'll divide this number by 0.8, and hopefully that will give me 67.6, which it does. I'll divide again by 0.8. You can see I already have these numbers here. I just want to verify that I'm correct. So I'll divide by 0.8 again, and I get 84.5. So I feel pretty comfortable. If I divide by 0.8 again, I should get the first term, which is going to equal 105.65. Now, there's going to be some rounding going on here. I'm just going to write 105.6, but I'm going to leave this in the calculator, the 0.625. So just so we're aware, that there might be some trivial differences. So it looks like I get 132 here. So now I can go ahead and answer this and say, it looks to me like the equation is he dropped the ball from 132 feet, and the rebound ratio was 80%, meaning he lost 20% of his bounce each time, and that would be the equation there. On to B, a major technology company, Expo Grow, is growing incredibly fast. The latest prospectus, a report on the company, said that so far the number of employees Y could be modeled with the equation 3 times 4 to the x, where x represents the number of years since the company was founded. How many people founded the company? Well, it starts at 3. So I would say at time 0, when the company began, it began with 3 people. So 3 founders. And then how could you describe the growth of this company? Well, the company grows by a multiple of 4. So it grows by a multiple of 4 each year, right? This could have been monthly or whatever, but it's each year we quadruple. I never said a multiple of 4 each year. All right, so a company virus is affecting the technology center in such a way that each day a certain portion of the virus-free computers is infected. The number of virus-free computers is recorded in the table at the right. How many computers are in the technology center? Well, it looks like 27, right? There's 27 computers there, and none of them were infected at the beginning. So 27 computers. And it says, what portion of the virus-free computers is affected each day? Well, this is the uninfected computers, so this is kind of actually asking the opposite. So it looks like a third are getting infected, right? If 2/3 remain uninfected, then 1/3 get infected. So how many computers will remain virus-free at the end of the third day? Well, it looks like 8, right? I'm just multiplying by 2/3. So divide by 3 times by 2. So divide by 3, I get 9, times 2 is 18. Divide by 3, I get 6, times 2 is 12. Divide by 3, I get 4, times 2 is 8. And that's what I get for that solution there. It says, as part of a major scandal, it was discovered that several statements in the Expo Grow prospectus were false. If the company actually had 5 founders and doubles each year, well, if it had 5 founders and doubles each year, we would just use this equation instead. I think at this point I'm going to open the next one to try and get 822. So let me see here. Okay, so kind of have a clean version there of 822. It says most of the exponential equations you've used in this course have been in the form y equals a times b to the x. So explore the student tool. Click the lower right corner of the graph to view it in full mode. So let's just go through back to Desmos, and I'll just add another slider here. Kind of cool when you put a letter there, you just add a slider. So when I move A, and I think we know this, A is just going to be the starting point, right? Where this thing crosses the x-intercept at. So it can cross at 1, or it can cross at 2, or it can cross at 3. And just like with B, we sort of have some kind of interesting things happen if we go negative with this. So I don't want to, it kind of turns it to a negative curve. I don't want to focus too much. We're not going to do too much of that in this class. We're going to focus more on the positive. So, and then like we said, the B, we know that makes it steeper or it makes it flatter. So that's what the A and the B do. It sort of changes either the y-intercept, the starting point, or it makes the multiplier either steeper or flatter. We're either multiplying by a bigger or smaller number. How can I identify the A by looking at the table? Well, the A is going to be the 0 term, like we said. And then how can I determine the B in each representation? We already did that. We're going to use a little bit of algebra, right? Just write that equation. A number times another number equals the next number. And then we have our B as well. So multiple representations web, it says, what connections are you sure you can make in the exponential functions web? Well, that's for you. This should say equations right here, right? So I don't know. Are you comfortable given an equation? If you do, can you make a table and vice versa? Can you make a graph if you have an equation? I think the word problem is always the trickiest, the situation. But so kind of think for yourself where you feel comfortable and where you don't feel comfortable. And hopefully as we go through this chapter, you'll have this thing completely filled in and you'll feel very comfortable with these kinds of equations. And then finally, I think this is the last one right here. It says, how can you sketch the graph of an exponential function directly from its equation without making a table first? Well, I know that if I have this graph, this thing's going to start at 7. I won't get very far into this. But I know it starts at 7, right? So 0, 7, and then it just starts doubling. So at 1 I get 14, and at 2 I get 28. So I'm going to get that steep curve for sure, and it will look something like that. So I know that this is my starting point, and that this is my multiplier, so I can just sort of do the table in my head.